After our class, we will continue study of fluid statics. Tuesday afternoon, we have lunch. We need to study fluid at rest, that's fluid statics, and we review what's the surface force, what's the body force, and we have, thank you, good afternoon. We have known the very important it's very important. Always vertical to the surface and point into the surface. Any point pressure is independent of orientation. What does it mean? We just, we give a very simple verification and we just show you, let's show you and then we go back, okay? Just 1 second, sorry. Okay. Just like here, okay, the pressure is always perpendicular to the surface, okay? Pressure will be always perpendicular to the surface. The surface pressure perpendicular to the surface, always perpendicular to the surface, okay? And pressure also is independent to the rotation. That means just like here, like this point, intersection point, from here, the pressure should perpendicular to the surface and point to the surface. It's 445. No, I think it's 445 already. Yeah, it's 445. Okay, so it's okay. So, and from this here, from this surface pressure also perpendicular to the surface. And at the same point, the pressure should be equal. P1, P1. Okay, this is what we mean. First, pressure will be always perpendicular to the surface and point to the surface. And then the pressure will be independent of rotation. Okay, I need to record. And so today we will continue study to find out the pressure under the action of gravity force. Okay, just for example, here is a glass of water. We need to find out the pressure at this red point, how to calculate it. Okay. Oh, forgot to, sorry. Let me, I forgot to, sorry. I think there's something wrong with my computer. Okay. Okay, I need to start from here. Okay, so let's start. Because I forgot we need to start from the equilibrium of a fluid element because we study fluid at static. We study fluid at rest. So that means a fluid element is the equilibrium station, right? So we take a cubic fluid element and then we draw FBD. We assume that at the central edge of the cubit, the pressure is P, okay? We assume the pressure at the central edge is P, and then using Taylor series expansion. Do you know Taylor series expansion? Do you know Taylor series expansion? You should have learned this in your calculus or right? Taylor series expansion is just like this is X, this is Y plot, and this is a curve, and we have here we have this point, we have another point, okay? And then we need to find out the value of this y x plus dx. And then this is yx, right? And if it's linear, we can find out y x plus dx will equal to yx plus here. Can you find out this one? This is delta y, right? We can find it's delta y, delta x, right? And so if dx goes to 0, and we will have yx plus dx equal to yx plus dy dx, right? This is Taylor series expansion, but for most functions, they are not linear. They're not linear. That's why we not only have the first order, we also have the second order and the third order. But if the dx is small enough, we can assume that it's linear. We mean the function here from y to yx plus dx is linear. So this is we often do. We ignore the higher orders and we use this Taylor expansion to find out the other values. We assume is p, the value is p, and so the value, the pressure at the one surface, the pressure at the center of the pressure should be P plus the spatial derivative dP dy times the distance to the centroid. That will be half dy, right? And then times the area, delta x, delta z is the area of the white surface. It will be the pressure force acting on this white surface. Similarly, for the left surface, we just can find out the pressure at the centroid of the left surface should be P minus dP dy times delta y over 2, because this one is the spatial derivative, this is the distance to the centroid, okay? And times the area, because we assume the cubic element is small enough that the pressure is uniformly distributed on the surface, okay? So we got the pressure force acting on the left surface. Similarly, we can widen in y direction and in z direction. This is Taylor series expansion, okay? So in x direction, we got p left, p right. Sure, here we use dx dy dz. This is x direction, this is y direction, z direction. So left, the pressure force, here should be capital P, okay? We use capital P to indicate the pressure force, small p to indicate the pressure, okay? Pressure is pressure force per unit area. Okay, so this is the force, surface force acting in the x direction, and the body force are also given in x, y, z components. Here, x, y, z is the body force per unit mass in x direction, y, z direction. So in x direction, the body force will be capital X times the mass. The mass is equal to the density times the volume. Volume is equal to dx dy dz, the volume of the cubic, right? Similarly, we got the body force in y direction, the y component of body force, it should be capital Y times rho dx dy dz. And in z direction should be capital Z times rho dx dy dz. And so in total, in x direction, the forces on this cubic element will include surface force and body force. And this part is the surface force, right? Sorry, this part is surface force in x direction. Surface force in x direction, this is a positive x. So this is the pressure force acting on the left surface, right? And this one is acting in right surface, okay? And that's why here got minus, because this force is opposite to the positive x-axis. And except the surface force, we also have the body force, okay? So this is a body force in x direction, the x component of the body force. Here, capital X is the body force in x direction per unit mass. Okay, so we organize this formula, this P cancel, and the dp dx half dx finally we will get, and also dx dy dz cancel dx dy dz, right? Sorry. So finally, it will be simplified to dp dx equal to zo x. Similarly, in the y and z direction, we got dp dy equal to zo y, dp dz equal to zo z. Okay, dp dx is actually the spatial derivative of the pressure in x direction. And dp dy is the spatial derivative of the pressure in y direction and the pressure derivative in z direction, okay? And here again, x, y, z is actually the x, y, z component of the body force per unit mass. This is called Euler equilibrium equations, which is found by Euler 1775, okay? So it's what it tells us. It tells us here from calculus we can just write down this way. This is partial derivative. This is the full derivative, right? We can write down this way. But if you just forgot what you have learned in calculus, you are not good at this formula. It doesn't matter. You just use this. It's enough, okay? For this formula, this Euler equilibrium equations told us in static flow, when fluid is at rest, the pressure change in space is due to the body force. Or we can say because of the body force, the pressure change in space. You say dp dx, dp dy, dp dz is actually the spatial derivative of the pressure. And also, we can tell from these equations that pressure increase in the direction of body force, right? Pressure increase in the direction of body force. This is what we are familiar with. Just have this common sense. When you dive into the sea, as you go deeper and deeper, the pressure you will feel more difficult to breathe. Why? Because the pressure of the seawater, right, increase in the direction of the gravity force. Okay, so this is Euler equilibrium equations is very important. Later on, we will use it to solve more phenomena. Okay, so here we need to introduce a term, equipressure surface. What's equipressure surface? From the here we know this equi means equal, right? Equipressure surface is a surface in fluid with same pressure. Okay, So free service. What's free service? Free service means the liquid, the interface between the liquid and the air. That's what we call the free service. Okay. Free service is everywhere have the pressure of the atmospheric pressure. So free service definitely is an equal pressure service. Equal pressure service will be always vertical to body force. Why? Why it will be always vertical to body force? Because here we say it's due to the body force that the pressure change in space. If there is no body force, there will be no pressure change. So equal pressure surface which have the same pressure everywhere will be always perpendicular or will be always vertical to body force. Okay. So if there is only gravity force, the equipressure surface will be horizontal. That's why when you hold a glass of water and the water surface, the free surface is horizontal. That's for sure, right? And if you just is just for example here, this if it's horizontal, so we know this is called free service. Free service is the interface between the water or other liquid with the air. This is called free service. And later on, we will use this to indicate its free service. Okay, free service should be horizontal. However, if this glass is set on a slope, so the free surface will be which one? Should it be like this one? Or should it be this one? Can you tell me? Should it be this? Or should it be this? Should it be the dashed line or solid line? The free surface is also the equal pressure surface. Which one? Can you tell me? Can you try to tell me if this is glass water, put on the slope, the free surface should be the solid line or the dashed line? There is no solid line. Dashed line. You can do this experiment. It's very easy. Okay, just for example, you just just because we are not face to face, because you can hold a glass of water and then you just begin to turn it, and then it will, yeah, it should be the solid line, right? You can show it by yourself. It's easy. Why? Why? Because the free surface is equal pressure surface, and it will be always perpendicular to the body force. Here will be perpendicular to the gravity force. You can draw FBD because it's fluid at rest. It's fluid at rest. It's static. And so you can write. Later on we will do more. Okay. But you can easily verify this. Okay. Okay, so under gravity, the pressure distribution will be like what? And it's easy. And we know the basic rule is the unit equilibrium equation, right? And so here, because the gravity force is downward, is in z direction, right? In z direction, we only have g, right? The gravity force. Well, g is the body force per unit mass, right? G, the acceleration is actually the gravity force per unit mass, right? Okay, and we know the x component, y component equal to zero. There is no gravity, there is no body force in x or y direction. So we got dp equal to rho z dz. We have dp equal to minus rho g. Why there is minus? Why there is minus? Because here, when you establish the coordinates, we just upward as positive, but g is downward, is negative, right? Is opposite to the positive z-axis. That's why here is minus rho g. So we integrate. Okay, it's a simple integration. Use what you have learned in calculus. It's simple integration. We got a b divided by rho. Rho is the density plus gz is constant. Okay, p over rho plus gz is constant. We know gamma. Gamma is called the specific weight. Gamma is called the specific weight. Specific weight gamma is equal to rho g. So instead use rho g here. We have p over gamma plus z equal to constant. That means at any point, we always have P over gamma. P is the pressure plus Z. Z, what is Z? Is Z? You say this is your x-axis. This is the axis. Okay, this is the arranging. Okay, and should be equal to constant. So how to find out the constant? How to find out the constant? We need to use. We call it boundary condition. Yeah. No, Z is the coordinate. Z is a coordinate. Z is a coordinate. You see here, you say this is the calculus. We have this, or you use here dp dz equal to rho g, right? In x direction, dp dx equal to zero because no body force in x direction. dp dy equal to zero. No, there's no body force in y direction. That means the pressure will not change in x direction. Pressure will not change in y direction. All pressure will be equal in the horizontal plane. Okay, in the plane parallel to horizontal, right? So pressure only change in z direction because we got body force in z direction. Okay, this is owner equilibrium equations, right? And so from here, from this one, use what you have learned in calculus. Use what you have learned in calculus. We will know that P should equal, we use, let me do this because I know some of you have forgot what you have learned before in calculus. So here we do the integration. This will be P not no limit. Here we use P not free service. And this one will be P everywhere. P is everywhere. And so if you, the origin of the coordinate system is the bottom of the origin, okay? This is origin. And then, so this P naught will be Z naught, right? And this one will be here, the reference point is Z, right? Got it? And then we will have this. This P naught, Z naught is actually, we call it the boundary condition. We know the boundary, right? We know the definition of the boundary, okay? This is a boundary condition. We know the free service. This is a free service. We use this symbol. We use symbol, this triangle, to indicate the free service. That means this is the interface between the water and the air, or between the liquid and the gas, or between the okay, this is a free service. Okay. And then we know at the free service, the pressure should equal to the atmospheric pressure. That means P naught is given equal to atmospheric pressure, right? And so use the boundary condition. Finally, we got P is equal to P naught plus rho g, Z naught minus Z. Z naught minus Z, we use H. H is actually the depth to the free surface. Okay, H is actually the distance, the vertical distance to the free surface, right? H is actually the vertical distance to the free surface. We call the depth. We name it the depth. And so P, the pressure at any point in this glass of water, is equal to P naught. This one is equal to the atmospheric pressure plus rho g h. This pressure is due to the liquid weight, is due to the body force, is due to the liquid weight actually. Okay, and we use specific weight gamma equal to rho g. So finally we got P equal to P naught plus gamma h. Okay. Here, one more thing, we widen the equation use this way. You will say we have addressed this at the beginning of this class that every term should have the same dimension, right? Here, Z is the dimension is length, right? Z is the dimension is length. So P over gamma also have the length, also have the dimension of length. You can check it out. P over gamma also has the dimension of the length. And then we call P over gamma is called the pressure head. And Z is called the elevation head. P over gamma plus Z, we call it piezometer head. Okay, we call piezometer head. Later on, we will use it. Okay, but here, maybe you just need to know under the gravity and the pressure will equal to at any point will equal to the pressure at the free surface plus gamma times H. H is actually the depth to the free surface. Okay. This part is actually due to the weight on top. From this equation, we say any point with the same depth h under free surface has the same pressure. That means it is also an equipressure surface. We know that's for sure free surface is an equipressure surface. So we know that equipressure surface will be always parallel to each other, right? Equal pressure surface will be always parallel to each other. This equation will apply to incompressible flow. Why? Why it only apply to incompressible flow? Because here, rho is a constant here. When we take the integration here, when you do the integration, when you integrate to have this formula, we regard rho as a density, rho the density as a constant. So when you use this equation, you need to remind yourself here rho is a constant. That means it's incompressible flow. And also here we only consider the gravity force. So gravity is the only body force. Sure, later on we will introduce, we need to include more body force, okay, but here only gravity force, and it's same fluid. It's very important. It's the same fluid, okay. That's again, it's the same fluid. That means the density everywhere is the same, okay. And it's continuous. That's for sure. And we know that for this course, we assume that the fluid is continuous. We don't study fluid molecules. We study fluid element or fluid particle, which include thousands, 10,000, thousands fluid molecules. Okay. And we can say the variation of pressure with depth. Yeah, we know in middle school that pressure in a fluid at rest is independent of the shape of the container, and pressure is the same at all points on horizontal plane in a given fluid. You see here, the pressure A at point A, the pressure at point B, the pressure at say D, E, F, G should be always the same. Why? Why PA equal to PB equal to PC equal to PD? Why this? Why? Because we know the pressure for this fluid is incompressible, same fluid, and it will equal to the pressure at free surface plus gamma or rho g. H will be the depth to the free surface. You see, because A, B, C, D, E, F, G, their depths to the free surface are equal, right? However, here we got mercury here. We got mercury here. So H and L, they are not equal anymore. It's very important here. Here we got the mercury. You say, do you know how to calculate the here? If we know the pressure at this point, we call Hij. If we know Pj, the sorry, if we know the pressure at point J, how to find out the pressure at H? According to what we have learned, the pressure at point H should equal to the pressure at J, right? Plus the density of mercury, right? Times G times this is H prime, right? The depth to the vertical depth to J, to the equipressure surface, H prime, right? Do you have any question about this? Yeah, I know most of you have learned this before in your middle school, right? So let's, you see, let's just like this one. I have vase. Yeah, I always like vase. We have this one, this shape, and this one. And I have this vase. Okay, this is A1, A2, A3. The vase, this is a water level. This is H1. I mean, this is H1. This is H2. This is H3. So we have the three vases. We have A1 equal to A2 equal to A3. That means the butter surface, the butter area, they are equal to each other. And also we have the same height of water. H1 equal to H2 equal to H3. I think some of you may already figure out this. in your middle school, but I want you to tell me, I want to know the pressure force on the bottom, pressure force on the bottom. This pressure force is P1, P2, P3. So can you tell me the pressure force is P1 larger than P2, larger than P3, or P1 smaller than P2, smaller than P3, or P1 equal to P2, equal to P3, or we don't know which one? Can you tell me the pressure force? Yeah, they should be equal with each other, right? Thank you very much. They should be equal with each other. Why? Because pressure force is equal to the pressure times the area of the bottom, right? And the pressure at the bottom is equal to what? Is equal to the pressure at the free surface plus the weight due to the water is equal to rho g h, right? H is the depth to the free surface. They are equal. So the pressure surface, the pressure force on the bottom of these three bars, they are equal, they are same. Okay. Good. Okay. So in real life, we always sometimes we always need to measure the pressure. Just like when I drive, we just need to the tire pressure should be at a certain value should be normal, right? And so certain pressure just here is set, certain pressure is given, and we can read from the panel of the car, right? The car panel. So the pressure is actually sometimes it's called the pressure is only 30 psi. What does it mean? Actually, here today we will need to know gauge pressure, what's gauge pressure, what's absolute pressure. Here, we got the local atmospheric pressure reference. And at point one, the pressure, we can measure the pressure relative to the absolute zero reference. This pressure we call absolute pressure. That means absolute pressure is measured with respect to absolute zero reference. But if I measure the pressure at point two with respect to the local atmospheric pressure reference, we call it the gauge pressure. It's a relative pressure. It's the pressure relative to the local atmospheric pressure reference. Just we know absolute error, relative error, right? Yeah, it's just like that. Just like your hat. Just say we say your hat is 180 centimeter. This is your hat. And if the average height of your class is 170 centimeter, so 180 centimeter is your absolute height, right? And if I say your relative to the average height should equal to 10. So 10 will be the relative height for you, right? So here, that's what we introduce, okay? Here we introduce gauge pressure. Gauge pressure is actually measured with respect to the local atmospheric pressure, okay? Sometimes, if the gauge pressure is minus, could be minus. Why? Because if the absolute pressure for point two is lower than the local atmospheric pressure, the gauge pressure should be minus, just like if a guy is only 175 centimeter. So relative to the average height, it should be minus, right? Nor shorter than the average height. So it could be minus the relative pressure relative to the local azimuth, but we don't like to be negative. So we use vacuum. We use vacuum to indicate the absolute pressure is lower than the local atmospheric pressure reference. For example, if the local atmospheric pressure reference is 760 mercury height, okay? And if from the point A, its absolute pressure is 1,000 millimeter mercury height, and so the gauge pressure for the point A should be 1,000 minus 760 watt. 760 should be equal to, this is its gauge pressure. But for point 2, if its absolute pressure is only 500 millimeter mercury height, and so instead of use gauge pressure, we use vacuum. Vacuum takes the absolute value. The gauge pressure should be minus, right? Sorry. Instead use minus, we use vacuum is 260. That means it's lower, the absolute pressure is 260 millimeter mercury height lower than the local atmospheric pressure. Okay, this is definition of the absolute pressure and gauge pressure. Okay, so in daily life, the tire pressure is actually is shown in gauge pressure. So if for here, for example, the tire pressure we say is 30 psi gauge pressure. So its real absolute pressure should plus the atmospheric pressure here. Okay, and also for the blood pressure, when you go to hospital, when you see a doctor, the doctor tests your blood pressure, the blood pressure is also shown in gauge pressure. Okay, so let's take 10 minutes break, and then we continue our study. Okay.